Hey, welcome. So, when you're trying to model something in the real world, with a pretty complex equation, how do you know for sure that a solution even exists? And hey, if one does, how can you be certain it's the only one? Well, today, we're going to unpack the mathematical guarantee that gives us that exact certainty for differential equations.
I mean, really think about that for a second. If you're in engineering or physics, and your model of a system spits out multiple possible futures, or maybe none at all, that's a huge problem. You need certainty. You need a guarantee. And that, right there, is exactly what the existence and uniqueness theorem gives us.
All right, here's our game plan. We're going to start with why we even need a guarantee in the first place. Then, we'll build our foundation on simpler first-order equations. After that, we'll use a really clever trick to handle second-order problems, apply our rule, and finally, we'll take a look at what happens when the theorem can't help us.
So why can't we just, solve the equation and see what pops out? Well, with differential equations, it's not always so straightforward. Before we sink hours or even days trying to find an answer, there's a formal theorem that can tell us right up front whether a unique solution is even guaranteed to exist. Think of it as our mathematical seal of approval.
Okay, so to really get a handle on the guarantee for the more complex problems, we have to start with the basics. Absolutely everything we're about to do is built on the theorem for these simpler first-order equations. This is our foundation. Let's dig in.
Okay, so here's the formal rule. Don't let it scare you. It just gives us two key conditions we have to check. First, the function f of xy has to be continuous. And second, its partial derivative with respect to y, which really just tells us how the function's slope changes as we move up or down, that has to also be continuous. If both of those things are true inside some rectangle, doesn't matter how tiny, around our starting point, then boom, we are guaranteed to have a unique solution, at least in that local neighborhood.
And I love this analogy. That little rectangle is our well-behaved zone. As long as our initial condition, our starting point, is safely inside this zone where everything is smooth and continuous, the theorem makes a promise. It says there's exactly one path, one single solution that goes through it. No weird jumps, no splitting off into different possibilities, just one clean path.
All right, that's great for those simple first-order equations, but what about the bigger, more complex second-order ones? Well, it turns out we can use this fantastic little mathematical trick. We're going to transform one really hard problem into a system of two easier ones that we already know how to deal with. So this is our target. It's a standard second-order linear initial value problem. And you'll notice we have two initial conditions this time, right? One for the function's value, y, and another for its derivative, y prime, both at our starting point, x naught. And here's the clever part. To get this into a form we can work with, we just define two new variables. First, we'll say y1 is just our original function, y. Simple enough? Second, we'll say y2 is its derivative, y prime. Now, by plugging these back into our original equation, we can rewrite that single, tough second-order problem as a system of two first-order equations. Now, I know it might look more complicated at first glance, but what we've actually done is put it into a format that our original theorem can understand. And this, right here, brings us to the aha moment. Because now that we have a first-order system, we can just apply the logic from our first-order theorem. We just need to check if those continuity conditions are met for our brand new system.
So let's ask the question, right, for this new system. What exactly has to be continuous? Remember the theorem? We need our new functions, let's call them f1 and f2, and their partial derivatives with respect to our new variables, y1 and y2, to all be continuous. So let's actually check them.
Okay, check this out. When we actually calculate these partial derivatives, something really amazing happens. For our first function, f1, the derivatives are just 0 and 1. Those are constants, and constants are always continuous. Then for our second function, f2, the derivatives are negative q of x and negative p of x. They don't depend on y1 or y2 at all.
So here's the punchline, the crucial point. The entire complicated-looking set of conditions for our system, well, it just boils down to one incredibly simple requirement. All we need is for the original coefficient functions from our equation, p of x, qx, and g of x, to be continuous on an interval that contains our starting point. That's it. And what that means for us is, as long as p, q, and g are continuous, we can always find that well-behaved box around our starting point. The theorem's conditions are automatically met, which guarantees a unique, local solution exists. Now, if those functions happen to be continuous everywhere, the solution might even exist globally. But the theorem itself only promises it exists nearby. It's an incredibly powerful result from such a simple check.
But what happens if one of those functions, let's say p of x, isn't continuous at our starting point? Does that mean there's no solution? This is a really important distinction to make.
This slide lays it out perfectly. If the functions are continuous, you get your guarantee. Check. But if they're not continuous, the theorem doesn't say a solution doesn't exist. It just says nothing. It's silent. We lose our guarantee. There might still be a unique solution, there might be tons of them, or there might be none. We just can't use this theorem to figure it out. And that really is the heart of it, isn't it? For these second-order linear equations, just checking for the continuity of those three simple functions, p, q, and g, that is the master key. It's what unlocks the certainty that your problem has one and only one local solution.
You know, the big idea here isn't just a rule about differential equations. It's a powerful way of thinking. We took a complex problem, we transformed it into something we already understood, and we applied a fundamental rule to find our guarantee. This pattern shows up everywhere in math and science. So where else might a simple rule solve the problem that seems impossible at first glance? It's definitely something to think about. Thanks for joining.